So folks, at this point in the semester, we've seen the graphs of our sine, cosine, tangent, and secant, and we'll add in the other two remaining trig functions soon. But I think it's time to start looking at transformations of trig functions. So it's very important that you have your basic shapes down, because now we're going to extend on that idea. So here, for example, you can see in this first problem, I want to graph the function f of x is equal to the sine of x. That's something we've done before. And then something new, I want to graph the new function g of x is equal to the sine of x plus 3. So let's see what's going on here. The difference between the two is that here we're graphing f of x, and here we have the same sine of x, and then what we have is a plus 3 being added onto the graph of a known function, or being added onto a known function. And so this is going to have the effect of vertically shifting the graph of sine up 3 units. And we'll sort of explore that. We'll see why. I mean, it's not magic. You can just go ahead and plug in values and you can see the effect. But what we want to do is sort of summarize these generic transformations so we can, without resorting to point plot, quickly sketch these functions. So the first thing I want to do is I want to go ahead and sketch the graph of the sine of x. So let's do that here. I'm going to let each x tick correspond to pi over 4. And ordinarily, I might make each y tick maybe something a little bit larger just so that my graph isn't too small. But because I want to compare and contrast these two graphs, let's let each y tick equal just the value 1. So I've learned my basic sine function. I know that the sine of 0 is 0. And if I go out, let's see, that would be the sine of pi over 4. If I go out, I know that the sine of pi over 2 is equal to 1, and so I'd be up 1 tick mark on that. So there's the ordered pair pi over 2 comma 1. And I know, for example, that the sine of pi is 0 and that the sine of 3 pi over 2 is negative 1. And so I'm plotting these known points on my sine function. And so let me sketch one base p. Ooh, that's not very good. Let's try that again here. So there's one period of the sine function, but I could continue going in the opposite direction. And you must. I ask you, when I give you one of these graphs, you get to pick what the scale is, but you need to fill out the entire graph. So it should all be filled in based on whatever scale you've chosen here. Okay. And so here I've got the graph of just f of x. Let me put that over here. That's kind of in the way. Let me put that over here as f of x is equal to the sine of x. So I've sketched the graph of this base function. I've actually done nothing new, folks. We've learned how to roughly sketch this. Maybe the only thing that's slightly new is that I'm giving you a blank coordinate system here, and you're having to decide the scale. But other than that, we've learned the shape of this basic sine function. Okay, so now, because we've learned the sine of x graph so well, we can now do this transformation of the sine of x graph. And this plus 3 that's being added to the output of the function is going to have the net effect of vertically shifting the graph up 3 units. Let's just check that. So, for example, we said before that if we were, let's go ahead and evaluate this function at pi over 2. So g of pi over 2 would be equal to the sine of pi over 2 plus 3. And we said before that the sine of pi over 2 we know to be 1. And then what do we do with that output from the sine function? We then add 3 units to it. And so the ordered pair that was at pi over 2 comma 1, if I continue my x tick to just be pi over 4, and my y tick I'm going to keep at 1. So the ordered pair that was at pi over 2 comma 1, when I plugged in pi over 2 into this transform function, I'm now getting out 4. That is, the y coordinate has had 3 units added to it. So here would be that same pi over 2, and now we go up 1, 2, 3, 4. And so there's the ordered pair pi over 2 comma 4. Now notice the effect that this has on when we input 0 into it. When we take g of 0, that would be the sine of 0 plus 3. That's just going to give me 3. So we're going to get this output value. And we could go ahead and label the other ordered pairs. You can check this, but all I'm going to do is I'm going to take each one of these plotted ordered pairs from before and add 3 to their y coordinates. So for example, this will now be the ordered pair pi comma 3. So let's see here, pi over 4, pi over 2, 3 pi over 4. So this is pi right here. And at pi, we've got a y coordinate of 3. And this was the ordered pair 3 pi over 2, which is, let's see here, so this was pi over 2, there's pi, there's 3 pi over 2, and at 3 pi over 2, the output was -1, but then we added 3 to that output, and so now the output is up at 2. And now I've got enough to get a rough sketch for the graph of this function. Let me finish this out. And so there's various ways you can see how I'm selecting these points, folks, and I'll let you spend some time studying them. But this is what we want to look at, folks, is these shifted sine functions. And so what you can see is that we've added 3 to all of these outputs, and this gives us the graph of g of x is equal to the sine of x plus 3. Okay? So what I'd like you to try on your own is I would like you to try this for the tangent graph. So you'll want to go ahead and sketch your tangent graph, and I'll help you out. I guess I'll sketch the tangent with you, but then I'll let you do this transformation on your own. So I'm going to, again, let my x tick be, I'm actually going to let, we'll let each x tick be pi over 4, and we'll let each y tick here. I think I've got enough room to do this, so I'll let each y tick be half a unit, just so the graph is a little bit more exaggerated. And so if we were to, say, take the tangent of 0, so if we take f of 0, that's equal to the tangent of 0, but that asks the question on the unit circle at an angle of 0, what is the tangent value? Well, that's the ordered pair 1 comma 0, and so as a fraction that would be 0 over 1 or 0, so the tangent of 0 is 0. Okay? And then remember that our tangents have vertical asymptotes at all of the odd multiples of pi over 2. So I'm going to go in and I'm going to sketch those next. So here is pi over 2. So I'm going to sketch this vertical asymptote here at x equals pi over 2. And then, let's see here, this would be 3 pi over 4, and there's pi, and then 5 pi over 4. And then here we would have another vertical asymptote at x is equal to 3 pi over 2. And if I were to go back in the other direction, here's a vertical asymptote at x equals minus pi over 2. And just judging by the scale here, we have 3 spaces in between. And so then I can draw another vertical asymptote at x equals minus 3 pi over 2. Folks, a quick way to see that the tangent is undefined at all of those odd multiples of pi over 2 is to notice if I went to try to compute the tangent for, say, this ordered pair, for this ordered pair right here, the tangent is the ratio of the y coordinate over x when it's defined, but I cannot divide by an x coordinate of 0. So every time I'm wrapping around my unit circle, I don't have a tangent at these 2 points every time I pass them. So if I go through the first time, there's pi over 2 and 3 pi over 2. Those are those two asymptotes. If I went the other way, I get minus pi over 2, or if I went the other way, I get minus 3 pi over 2, and that gave me those vertical asymptotes. So I've got the basic shape of the graph of the tangent function down. Notice that if we were to take the tangent of pi over 4, that's equal to 1. So there's pi over 4. And I said I'm going to let each y tick mark be a half, just because I've got the room to do so. And so if I plot all of these points, and we're going to learn more about this as we go along, we're going to get more sophisticated. But here you can see I'm just making copies because I know that the tangent is a periodic function. So here we would have our quick rough sketch of the tangent function. Now this is not new, What's maybe new about this is you choosing a scale and you having to plot this with the grid coordinates that I've laid out. We've done it without grid coordinates. But there's nothing new about the shape of this tangent function. So this is the f of x equals the tangent of x that we already know. And what I'm asking you to do here is to graph g of x equals the tangent of x minus 2. So pause the video, you try this. Okay. Folks, I'm not going to provide solutions to this, so you pause the video, you give this a shot. Notice what you're going to do here. You're going to use the same knowledge that we gained before. Here, this plus 3 added outside the argument of the function shifted all of the y values up 3 units. So the question you want to ask yourself is, what is this minus 2 going to do to all of the outputs? And if you're not sure, you can point plot a couple of times until you figure that out. So pause the video and work this question on your own. So folks, the last thing I want to do in this video is I want to make a quick summary of what we just saw here. So suppose you know the graph of f of x. Then if I were to create a new function, you could call it g of x, which is the old function plus d. This is just the graph of f vertically shifted up d units. Folks, I didn't quite give you enough room for that. I'm sorry about that. I'll fix that in your handout. But it's vertically shifted up d units. Notice if d is negative, this is what you should have found when you tried number 2 on your own. If d is negative, then the graph of f is shifted downwards. Okay. So if we think about these, so this knowledge that I just gave you here, folks, applies for any function. If I know the parent function, then just adding a plus d vertically shifts it up d units. Okay. If I want to talk specifically about the trig functions, then we can think of each parent trig function as having an initial midline, and that midline always starts out being along the line y equals 0. Then the graph of the new trig function, this should be g of x here. The graph of the new trig function is the old one added d to it. That just shifts the midline up d units. So that's what I want to point out here very last in this video. I could go ahead and sketch a dashed midline along this here, and I'm trying to draw it directly on top of the x-axis. So that's at the line y equals 0. I've got this midline. Now careful, that's not an asymptote, even though I'm drawing it dashed. That's not an asymptote. It's what's called the midline for this trig function. And you can see that the midline sort of passes midway between, for the sine function, it passes midway between this peak and this valley here. And notice that the midline is now at, let me scoot that over for you, the midline is now at the horizontal line y equals 3. So the midline started out at y equals 0, and it got shifted up 3 units. So while you didn't draw this one, we didn't draw this one together, you should have, you should see that I could think of there being a midline to this tangent equation right here at y equals 0, and you should have found that that midline got dropped down to y equals -2. So it should have just been this graph here shifted down 2 units, and if you were to just track what's happening along this midline and pin everything else and bring it down 2 units, you should have had, that should resemble the graph that you have. Okay, folks, that gets through the vertical shifts. In the next video, we're going to look at something completely different called vertical stretches. So here I'm going to graph 3 sine of x as opposed to the sine of x plus 3, and that's going to have a different effect. So I'll see you there in the next video.